Hey, what's going on? It is your boy Jay Bailey here, and I'm back with yet another video. And today we have another poem challenge from Hack the Box. It's called Bat Computer here. We are going to be taking the reins of Batman. We're going to be Batman today. We're going to save the world from the evil Joker because he's been acting wild, and we got to tell him got to tell him to chill out. You know, Joker can't just be out here running wild like that. As the description says, it's time to save the world. This is going to be a buffer overflow challenge, but as I usually do, I'll do my reverse engineering type of stuff first, and then we'll get into actual developing the exploit for the buffer overflow, and we will actually execute code, like our actually drop a shell this time. If you're not interested in the reverse engineering part, I'll leave a timestamp somewhere where you can just sort of skip ahead to the buffer overflow stuff. If that's all you want to see, I understand. But if you're interested in the actual reversing part, well, stay tuned. All right, well, let's get started here. As always, we're going to start by running the file command on our binary, which is called Bat Computer. And we see it is a 64-bit binary. It's Pi enabled. It is dynamically linked. And we also see it's been stripped of the symbols. Not very fun, but that's okay. We can look at the dynamic symbols with the -d flag here. And we see that not a lot of interesting things here. I'm not really sure what set vbuff does. I mean, I've read the description, but I don't quite understand what it does. So if anybody can tell me why you don't want to do this, I'd like to know, to be honest. Like I just didn't really understand why someone would run this function. We also see the read function is being called here, and if this is the function that's going to grab our user input, which most likely it is, then that's good because we don't really have to worry about bad characters, because the read function will continue to read stuff until it actually reaches the end of a buffer. So if there's no characters embedded inside of a buffer that we provided, it'll still keep reading until it reaches the end of our actual buffer that we provided to it. So that's good. So that means we don't really have to worry about any bad characters for this challenge. And I'll get into bad characters later on when I get into the exploit development stuff. Anyways, let's go ahead and look at the strings in here. And all right, so it looks like we have a prompt here, and there are two options. We can track the Joker, or we can chase the Joker. And we also see that after, I guess, they find the Joker, they locate him when they give us this address here. This is likely going to be important here. I mean, it's printing out a pointer to something, so it's most likely going to be an address of something important. Spoiler, it is going to be important. So I guess this is just something to keep track of. Like whatever gets put in here as a parameter is probably going to be something of very, very interesting to us. We also see another format specifier here, %s, and we see something that is honestly quite disappointing here. You would think Batman, the Dark Knight himself, would have a better password than this, but I mean, and then it's in the strings. He didn't even try to hide it. Like, Batman, you are the protector of Gotham. I'm sorry. It's just disappointing, you know, when like, your heroes, you know, like they're supposed to be. Anyways, let me calm down. All right, well, so we see access granted. We also see into navigation commands, and all right, nothing else interesting in the strings here. Next thing I'm gonna do is we're gonna run checksec on this guy, and as you noticed in the last challenge that we did, the poem challenge, it's gonna give us the protections that are enabled on this binary. And we see that it's pretty wide open here. So there's no stack canary, which is awesome. We talked about stack canaries before, so I won't go into it again, but it's just another mitigation for us to prevent us from doing a buffer overflow. There's also NX is disabled here, which is interesting. So these two things, I believe you have to actually go out of your way to do that. So the author wanted us to do the buffer overflow, obviously. And we also see there are sections that are read, write, and execute. And so that's most likely going to be the stack. And so what that means is that we can place code onto the stack, and if we can tell the binary to say, hey, this is execute these instructions next, this is going to execute them. And this is a very classic way of doing the buffer overflow. It doesn't work anymore, but it's a good way to just sort of get your feet wet into the buffer overflow type of thing. So let's go ahead and look at read elf -- segments here. Then we're going to call on the Bat Computer, and then see right there in black and white that the GNU stack is read, write, and executable. That's right, we're gonna be popping some shells today, ladies and gentlemen. So let's go ahead and open this up in Ghidra to do some more analysis. All right, and because as I mentioned, it's binary strict. We can't just go into the filter here and look for the main function because obviously it doesn't know what the address of the main function. So we have to find it ourselves here, which is it's fairly easy for this particular challenge. So we go to the entry point here, we see these series of instructions here, and we see this call to libc start main actually takes in the parameter of the main function as one of them. Go figure, right? And the parameter for his main is actually going to be this first one right here that gets placed into the RDI register. So I'm just going to go ahead and rename this to main here, and then just go ahead and double click it and let's go to it. And so now we're in the main function here. And so right off the bat, we see it calls this function here. This function is not very important. This function, all it does is it calls those set vbuff functions. So I'm just going to call this, I don't know, set buffers. I'm not going to go into the disassembly because it's really not that interesting. All it does is call set vbuff on standard in, and it has 0, 2, and 0 out the parameters, and it does the same thing, but it has standard out as the other parameter. So that's all that function is doing. Not very interesting, so I don't want to waste too much time on there. Let's go ahead and jump into the meat and potatoes, the main function here. All right, so this is going to be some kind of weird way of kind of keeping track of variables because, as you can see, Ghidra or the binary loads up this address here to the RX register, and then we increment that by 4. So we normally see stuff like that when we're trying to when we increment it, we're trying to get like the, what is it called, the index of an element. But in this case, we're actually getting an entirely different stack variable here, and because of that, we can't rename variables here in Ghidra because, well, Ghidra only sees this local 68 variable, and as you can see, it uses it pretty much everywhere down here because it thinks that this RBP minus hex 60 is just one variable when it's actually this is a one variable, but there are other ones as well, and the Ghidra can't see that because they're being offset by this thing here. So we're gonna have to keep track of it ourselves here. So we're just gonna go ahead and do RBP minus 0 hex 5C. I'm getting that because hex 60 minus hex 4 is 5C there. We're going to call this a variable here, and it gets loaded into this memset here, right? So we see that it gets loaded into memset, and the other parameter is going to be 0 and hex 16. So pretty much it's going to fill this string here. I'm guessing it's a string with 16 zeros in there. So we're just going to call this, it's not technically empty, but I guess it's kind of an empty string. It's just filling it up with zeros. Or maybe I'll just say string all zeros. Let's do that. String all, is it zeros or is it zeros? I'm going with zeros. So we're saying is that, and so the C for that would be string all zeros. Oops. And then 0 hex 16. Just like that. Yes, that looks about right. All right, so then as we see, it prints out the prompt here, right? It's just saying welcome Batman, and it prints out the options. And then we see another stack variable here gets loaded into REX, but this time it doesn't get offset at all. So this RBP minus hex 60 is obviously going to be our choice here, right? Because this is our prompt that says, track joker or chase joker. And if you go to this thing right here, we see that it's going to be %D. So we know that RBP minus hex 60, this variable here, is actually going to be an integer. So let's go ahead and we're just going to say choice is equal to RBP minus 0 hex 60. Whoops. 0 hex 60. And then we're going to say, what is that? I'll say a printf. I'll just say prompt just for short. And I'll just do the line. And then we're going to scanf %D. And then what is it? The address of choice, right? Looks about right to me. All right, and so then we see that it's going to take this and compare it to 1, right? So it's going to say if choice is equal to 1, it's going to do some stuff down here. So we're just going to say if choice equals to 1, we're going to do some things. Otherwise, we see there's going to be an else condition here. Else, we're going to do something else. All right, so let's see what it's actually doing here. So it grabs this thing in here again and it increments it by hex 14. So that's also going to be another variable there, right? So that's RBP minus 0 hex 4C, I think. It's going to be another stack variable. And that's actually going to get loaded into this place here where it says it was very hard to find whoever it was, but Alpha managed to do it. So this is going to be our, what's going to be our, and the parameters for this %p is this RBP minus hex 4c variable. And so we know this is going to be what the Joker's location, I guess. So we can just call this Joker, Joker location is equal to that. So if we go back here, we're just going to say printf, I'll just say %p because I'm lazy right now, and then address of Joker location. Whoops. There we go. And that's pretty much all that does there. And then we see it jumps back up here to this section here. So we know now this is going to be some type of loop here. So from all of this here is going to be inside of a loop. So let's go ahead and indent that for one. All right, so now we know that this is a loop, and I'm just going to say while true because we don't quite know what's going to break out of this loop. So like for right now, this loop would just looks like it's infinite because there doesn't seem to be anything that's saying break out of this loop. So let's see, maybe this is a condition here. So if we jump here, let's see what happens here. Well, now we're going to compare choice with 2 this time, right? So we're putting that into EX register and comparing it with 2. And if it's not equals to 2, then well, okay, it looks like it breaks out the loop here. So that's a condition there. So let's see if it come here. And we're going to say else if choice is not equal to 2, then I guess we can just say break like this, right? If it's not equal to 2, we're just going to break out of this loop. And I think we can just do this? But if it is equal to 2, then it's going to come down here and do these things. So it's going to say, okay, printf. I'm almost the password, so I'll just say password. And then we see that it's going to load up this RBP minus hex, was it 5c here? It loads that up into printf, or sorry, into this guy here. And then we see it's going to call it with this format specifier, which is %15s. So this is likely going to be our password. So now we can rename this guy up here to string out zeros. We can say, well, it's password now because it's obviously the password there, right? So this is going to be our password here. And so pretty much it looks like scanf %15s and the address of password, right? And then it compares it to Batman. I mean, he's not even my favorite character, but like you would just think someone like Batman would know better, you know? It's just, yeah, I don't know. I cannot be the only one that's disappointed right now in Batman because it's just, come on, the Dark Knight. You would think, right? But it's, I guess we all have our flaws, you know. What's the old saying? Don't look behind the curtain, right? I guess I shouldn't have done that. That's all right. So it compares it to that, and let's see. So let's say, okay, if it's not that, it's gonna say, so if it's not that, I'll just say else here. Else, yes. But if it is equal to the password, then we're gonna jump down here. And now it says, okay, enter the navigation commands. And then we see, again, it loads up this hex 14, and then we're gonna call read on our Joker location, also with hex 89 and with 0 here. So it's gonna like read. So obviously right off the bat, you might be able to tell that this is gonna be where we're gonna overflow the buffer here. And we know that because this is the only way we can input anything that's greater than, I guess, 15 characters here, and this is just 1 energy here. So this is literally our only option here. So obviously this is our buffer overflow, our buffer that we're gonna overflow to get our code execution. That's our vulnerable buffer there. All right. So this is pretty much what the code looks like here. Fairly simple, nothing too difficult. I guess I should add this because that's what it does. But nothing too crazy. So we know that we're going to have to give it the correct password eventually at some point, and then we can enter in our navigation commands. And once we do that, we have to break out of this. So we have to give it anything other than 1 or 2. So I'm just going to go with 3, and that'll break us out of the loop. So let's go ahead and confirm that we can actually crash a program by just writing 137 A's to the program and see what happens. All right, so what this is going to do is it's a one-liner that's going to insert 2 and then the password and then 137 A's, and it's just going to write those to the buffer or to standard out. And then it points it to this file here. So if I write a cat without the text, you see it prints out 2, bad password, and then all these A's. And at the end, it's going to be 3 there because we want to exit the program afterwards, right? So if I were to cat this and pipe it into our shell or our binary, you see that we get a crash there. And so that's really great. So that means we've verified that we have indeed discovered a vulnerability because right, we know that now we can at least get it to crash. So now we have to go through the steps of actually making it crash reliably, and then eventually we're going to make it crash to where we can execute our own code. So let's go ahead and open up GDB. All right, and remember, because we don't have any symbols, we can't just say break main because, well, the main function isn't there. And additionally, we can't when we do set a breakpoint, we're gonna have to use the pi, I guess, module to do it, because there's this pi enable binary and the addresses are going to be different when we actually run the program. So let's first find where the main function is in here. So we do info file, and the .text segment is the one we're interested in here because that's where our executable code is going to live. So if we do this, and I'm going to say I'm going to examine 12 instructions from this address here, and we see that we have some disassembly there, and this looks exactly like as we saw earlier. And we even see this thing here gets loaded into RDI, and we call this is going to be libc start main. And this is actually the address of that here. So this address is what goes in there. So we're going to say, now we're going to, just to be sure, make sure that that's the main function, examine 20 instructions from there. I could have did 12 again, but I just want to do a little bit more. And there we can see that this looks like our function prologue again. We see it's calling that set buffers, and then we see that it's doing exactly what we saw, right? So it's getting, this is going to be the password if I recall correctly, call that into memset. So yeah, so this is our main function here. Great. So let's do pi break, and we're going to break right here at 0 hex 11 ec, and then we're going to pi run, and we're going to pass in our exploit dev crash binary. And so the beauty of this is that when we step through it, it's actually going to insert in those characters as we go through the binary without us having to type it in ourselves. So let me show you what this looks like first here. So I'm going to go ahead and let's disassemble a little bit more of this. So let's go ahead and examine 50 instructions from here. All right, let's see. I want to skip to right here. I'm going to set another breakpoint there. So now, since we're actually running the program, we don't have to do pi break or pi run anymore. We can just run it here, right? So what's going to happen here is you see that it's loading this up onto the stack here, right? And at this point, the scanf call is going to ask for our input, but because we've already given our input with the Python, the Python's going to inject it into the code for us, all right? So like you'll see on the stack, and actually I'll step through it a little bit more so you can see the stack. So let's see. All right, so the stack is now created here, right? So this is going to be our stack here. You're going to see that when I continue, that the value 2 is going to be placed right here, because that's where RBP minus hex 60 just happens to be there. So let me go ahead and hit continue, and you see there it is. There's 2 there. So that means our code is working. Unfortunately, there's going to be a part where we're going to have to do some finagling. So I'm going to go ahead and set a breakpoint right now in anticipation of that. So let me go ahead and I think this is it. So I'm going to have the breakpoint right there, and you'll see what I'm talking about when we get to that part of it. But right now we don't really have to worry about it too much. So I'm gonna go ahead and continue. Let's see, we're breaking there, and we hit continue again, and you see that now it has 3 in there, right? And now we also see that it filled in our buffer with a bunch of A's. So let's go ahead and start one last time. I'm gonna execute 50 instructions from here now. Actually, I can just do RIP like this. And I'm going to stop right here. I'm going to stop right there. Let's go ahead and hit continue. Hit continue. All right, there we go. All right, so now we're right at the leave instruction, and I want to talk briefly about this because this is a little bit different than if you ever done a buffer overflow on a 32-bit binary. It behaves a little bit differently, but essentially it's the same thing. So on a 32-bit binary, once you exit a program, you would notice that your buffer will be filled into this RIP register, or actually in 32-bit it'd be EIP register. In this case, you're not going to see that happen because the ret instruction is what's going to tell the RIP where to actually execute next. So it's going to say begin executing instructions at wherever the stack pointer points to, at the address the stack pointer points to, right? And because we're going to insert some bad actual addresses, that it's not going to point to anything. So I'm going to show you that really quickly. But first I want to talk about what this leave instruction does here. The leave instruction does two things. It sets the RSP register to the RBP register here, right? So these two are going to be equal to each other, so they're going to have the same value. They're going to point to the same thing. And then it pops RBP off of the stack. And that also does two things. That's going to place a bunch of A's, there's going to be 8 A's into the RP register, but that also increments the RSP register by 8. And it'll all kind of fall together as we go through it. At least I hope it will. And that's important because remember, the RSP register is essentially going to point to the return address. That's going to be our return address. So if I were to look at the stack now, I can examine it here. Oops, I want to start from the stack pointer here. We see that this is our stack and we've corrupted it. So if we look at the address of RBP, which is right here, and we see that we've overwritten it with all of these A's. And remember, it's going to be, when we execute this leave instruction, RSP is going to point to right here. It's going to have this as its address there. And obviously that's not a valid address. And so when we do the return instruction here, it's going to segfault. So let's go ahead and do this really quickly. So little step instruction. And see, just as I said, that it has this in there. And this is the same thing as this previous RBP, but plus 8, right? Because we scroll back up here, RBP was, I'm just going to say at the end, hex 40 here, right? DC hex 40 or DC 40. You see here it's DC 48 because it's incremented by 8 after it popped it off of the stack there. All right, and so then of course if I were to try to step again, we get a segmentation fault because this is not even in an address there, right? Okay, so we've caused it to crash and we have a better idea of what's going on. Now we need to actually create a unique string to place in there so that when we execute the binary and we overflow the stack, we can see where does this live? What offset do we get to this string here? So that way we can then say, okay, now let's try to overwrite it with something actual, like a valid address, and see if we can get to it. And hopefully it'll make sense in a few seconds. So let me go ahead and create a unique string here. So I'm going to MSF pattern create, and we're going to do 137 here, and it creates this unique string here. And I've already kind of done this here, so I'm going to cat dot exploit dev, and we're going to do get offset here. So all I've done is the exact same thing as the previous one. The difference here is that now we're going to put in our unique string, so that way we can get the offset of this unique string once we do our once we place it in this binary here. So let's go ahead and run. And remember, we don't have to do with the py run anymore because we're already running it. And another great thing is that these addresses are going to remain the same too in between each run. So that makes it a lot easier to keep track of things. So if we're going to get the offset here, and you see that now we have this unique string. So hit continue, it's going to bring us to this leave instruction here. And now again, I'm going to say examine the stack. And let's see, RBP is again hex 40, and here it is. So this is going to be the base pointer here, and this right here is going to be our return pointer. So what we can do is we can copy this value here. Actually, let me just go ahead and step through this one time. You can see that again, that's where it points to, and then of course we get the segfault. So now we have that value. So now what we're going to do with that is we're going to say MSF pattern, instead of creating, we're going to do pattern offset 137, and we're going to give it we're going to query for that particular address or that particular string of bytes. And so that's going to tell us where does this string of bytes land in this buffer. Like what offset does this thing come up in this buffer here. So if I do that, and you see it's an offset for 84. All right, so now we can test this out, and we're gonna do a little fine tuning here. So again, we're gonna cat exploit dev. This time it's going to be, I think I call it test offset. Yes. So now I'm gonna write 84 A's because that's gonna reach right to the RSP register, and then I'm gonna put some B's there, 8 B's there, and that's gonna make sure that when we overwrite, it's gonna overwrite with a B. So making sure that we are indeed overwriting the right pointer, because if not, then we have to do a little more experimentation. Let's go ahead again. It's going to run it. Continue again. And so now this is where it kind of becomes a little bit annoying. And this is what I mentioned earlier, right? So what should have happened is that 3 should have been updated here, but for some reason, I don't know why, it's not being updated anymore. So now instead of when we get to this, when we get to the instruction where it does the comparison right here, it's going to compare to 2, and that's going to say, okay, well, it is 2, and it's going to look for our password. We wouldn't have the right password now, so it's going to exit out the program. We don't want that. So what we have to do is set the RX register to 3. I'm going to cheat here, then I can continue, and you see that we move past it. All right, so now one more time, we're going to look at the stack here to see what we've done. And you see that, look at that, we successfully overwritten the stack pointer there, or the return address there, right? So then if we step again, we see that there it is. It's just 4 Bs, or 8 Bs, I apologize. And of course, again, we get a segmentation fault because this is not a valid address. All right, great. So what if it was a valid address? Let's see what happens. So again, let's just run this really quickly. And we can do with any of our inputs that we've done. I'll just do it with the same one again. And what I'm going to do now is I'm going to see what is the address of our buffer, of our vulnerable buffer. And then we know that it's going to be RBP minus hex 4C. So I'm going to say XS RBP minus 0 hex 4C. And that gets us this address here. So now what I'm going to do is I'm going to update. So I'll have, what did I call it? Overwrite RSP here. So now I have 84 A's again, but this time I have an actual address in there. And I'm going to have to update this because, well, as I just said, this is, as you saw, this is a different address here. So if we change it with the correct address, we will get the we should point to our vulnerable buffer, and that should actually give us not code execution yet, but it'll at least say that we're going in the right direction. So let's go ahead and update this here. So I'm going to go ahead and copy this, copy paste for these values here. So it's going to be F4 and then DB, and then everything else that looks the same. All right, so I'm going to go ahead and run that. And now let's go ahead and do this again. It is overwrite RSP. All right, so now this is going to be a fundamental difference here. Now earlier you saw that it pointed to a hex 40 with 42, 42, 42, 42, 42. This time what's going to happen is it's going to have the address of our buffer here. So it's going to have an actual address here, and that's going to point to a bunch of age, which is the rest of our buffer. It's still going to give us a seg fault because of course those aren't valid instructions, but it's at least going to show us that we are going in the right direction. So let me go ahead and do this for you really quickly. So now you see that this is different here, right? So now you see that it points to an actual valid address, but these are not valid instructions here. And then you see here, even the ret looks different here, right? So now the ret's like, oh yeah, this is a valid address. So I'm going to tell the binary to execute instructions at this address here. But of course, if we try to step, then we get a segmentation fault, which is what we expected. So now we have that. So now all we have to do is put actual valid instructions in there. So let's go ahead and do that. But we still have to, so I have the same code here. I think I'll call it spawn shell.text. So now we have to update this with the actual correct address here. So let's go ahead and copy paste, and let's update the address here. So this here is going to be our shellcode. And our shellcode is this one's only 29 bytes, and I found the shellcode, and I'll put in the link in the description. So we're going to change the address to, let's see, F4 and then DB, right? F4 DB, yes. All right, now if we do that, we're going to put that in there. All right, so now again the same thing's going to happen. But again, the fundamental difference is now there are going to be valid instructions there. So that you'll see it right away. When we step into it, we see that we have overwritten the address there. There are a bunch of knobs, and oh, this is not correct actually. What's going on? This should have been our instructions first, which is strange. And I just realized the reason why it wasn't working is because I never actually overwrote, or I'm not using the right one, right? Because see here I'm just saying spawn shell, right? Where this I'm using the old spawn shell, I guess, of which I'm not overwriting the correct one. So now I'm sorry. Now it's going to work for sure. All right, there we go. Yeah, so this these were instructions I was expecting here, right? So I have my shellcode there first. Jeez, yes, we have our shellcode followed by our no operations. So this is gonna, so as I was saying, our shellcode isn't gonna be as long enough to actually fill up 84 bytes. We have to fill it up now with an extra 55 bytes of, these are gonna be NOPs here. And then we tack on the actual return address there. And now if I hit continue, I'm gonna scroll up here, you see that we executed this program. And so now we verified that we can get the exploit working, but this is only in GDB. So if I were to try to run this outside of GDB, of course, it isn't gonna work for a few reasons. So if I do this and I wanna do spawn shell, well, actually, I should do it from right here, right? Because now this has the updated address, spawn shell. And then we're gonna /bat computer. And we see, well, it doesn't work mainly because that it doesn't insert the 3 character as we wanted to. But even if it did, it wouldn't actually give us the shell because, well, it doesn't have the new address in there. Luckily though, the binary gives us the address in there. So all we have to do is we call the functions. I'm actually gonna show you my code here. So what this is gonna do here, we can define our shell code, and we're gonna eventually build our payload here. So then we just, whoops, this is the remote exploit there. That's all right. So the local one, we have to test our exploit first. So locally, so again, our shell code there. We're gonna interact with the process there. We're gonna grab the address. And so I've actually never ran the program for you all. So if I do bat computer, and I'm gonna do 1 there. So this is going to grab this line here, and then this ugly thing here is going to get just this particular address right there. It gets the 0 hex and all this other good stuff there. And then it just prints it out. And then we begin building our payload, right? So we protect the shell code first, our NOPs, which is the length, which is 84, which is the length of our thing, our buffer, minus the length of the shell code. And then we tack on the buffer address. And then we send 2, we give it the password that we're very disappointed at Batman for. And then, can you tell I'm salty about that? I'm just a little salty about that password. And then we send the payload, and then we have to actually get out of the program, so we send 3, and then that's gonna cause the binary to crash, and then we get the interactive shell. So if all this works, we should be good. So let's go ahead and try this now, Python 3 local exploit. And there you go, we got it. Oops, there we go. All right, so now we have a shell on our local machine. So we verified that this exploit actually does work. So now we have to do the same thing for the actual remote machine. The only difference here is that we have to start a netcat process here, and then we have to, of course, specify the IP and port, but everything else is pretty much exactly the same here, right? So let's go ahead and start the instance here. So I'm gonna jump here, and we're gonna start our instance. And then we're gonna copy this guy, and we're gonna replace this IP with import with the correct one now. So now if we run our remote exploit now, we should get a shell. Oh, there you go. And we got a shell. And so now we can cat the flag, and there it is. Love your shelf. You saved the world. Good job, everybody. All right, and that is pretty much it. This code here is available on my GitHub. The link is in the description below. Jesus. So you can go ahead and check it out at your own, at your own will. But yeah, that's pretty much it. So we've successfully done another buffer overflow. We executed some code. Now, the only reason why this works is, remember, because the protection on this thing are pretty much non-existent here, right? So no stack canaries, NX is disabled, and the stack is actually executable. So if this were not true, then obviously this would not be as easy as we just did it. But that's all I have for today. Hope you guys learned something new. Hope you enjoyed the video. If you did, I'd love a like. That'd be really awesome. If you have any questions, if there's something that didn't make sense to you, if I didn't explain something very well, that's very likely because sometimes I aren't the best at explaining things. Leave it in the comment section below, or you can hit me up on Twitter, Instagram, Discord. I'm pretty available in a lot of different places, so if you want to reach me, you can reach me. If you like this content and you want to see more of this type of content, do not forget to subscribe and hit that bell icon to notify when the videos go live. I'll see you guys in the next one. Peace out.